Once we know an equilibrium constant, we can apply it to a new situation. For the following reaction, our absolute favorite one, we've calculated a Kp of 0.121 at 80 degrees Celsius. We can use this value now to determine the equilibrium concentrations based on initial concentrations. So we can say if we put 4 atmospheres of NH3 in a sealed vessel, what are the equilibrium concentrations, pressures rather, of hydrogen and nitrogen? We can do this. Now that we know our constant, we can go ahead and solve for it mathematically. We know that the equilibrium expression tells us that the ratio of products to reactants must always be the same. And so we know that since we know what that value should be, that ratio should be, once we're given an initial one, we can figure out how much of that is going to either combine with other reactants or break down as a product. In this case, we put a product in. You could put both reactants in. We could start with 4 atmospheres each of hydrogen and nitrogen and figure out how much ammonia we've made throughout the course of the reaction. Not through stoichiometry, but through equilibrium. And how we do this is we're going to use something called an ICE table. So generally speaking, we typically will, we can go ahead and keep it as this. We'll copy our equation down, and we will construct what's called the ICE table. So I stands for initial concentrations. So our initial concentrations here of hydrogen and nitrogen are 0. We have 4 atmospheres of ammonia, that's it, nothing else. So we have our initial conditions, whether those are concentrations or pressure. We know that there's a change of concentration happening. We know that ammonia is going to be breaking down because in order to reach equilibrium, that's what's going to happen. We have no reactants. We know that the ratio has to be 0.1 to 1. So we need something in the denominator, right? Doesn't make sense otherwise. Can't have 0 there. So we know that we're going to break down some ammonia. And I'm going to put a 2 there because we have a coefficient of 2 in front of ammonia. For every 2 ammonias that break down, we're going to get out 1 nitrogen and 3 hydrogens once we have this out here. And so that's I and C. So I is our initial conditions. C is the change that's happening. We're breaking down our products. We're forming reactants, each of them to their respective coefficients. And then the equilibrium would just be the sum of the 2. If we add these 2 together, the I and C lines, we end up with the equilibrium concentrations. And so, what's the point? Well, thankfully, we know that we have an expression for this, right? We have the pressure of ammonia squared over the pressure of hydrogen cubed, and then the pressure of nitrogen. That's our Kp. We can simply plug in these equilibrium values that we found. We know that we have 4.0 minus 2x squared. We have 3x cubed, and then we have x. And we know that all of this equals to 0.121. That's a mathematical value. So we only have one variable now. It's a giant pain in the butt to solve this variable, but we can. And we're going to continue this in our next video, where I'm going to show you how to use an online widget to do the calculation for you. Because if you want to solve for x, that's going to be a big pain, because we're going to have an x to the 4th option. which is not going to be easy to solve for algebraically. So we'll show you in our next video how to use Wolfram alpha to calculate this value of x. And once we see the value of x, we can simply plug it in to these 3x, x, and 4 minus 2x. We can plug it in there and we'll determine our equilibrium pressures. So go ahead and start watching that.